3 equal masses are connected at equal distances along a rod of length 3L, and that rod has a negligible mass. The moment of inertia about the left end of the rod, well, what's the moment of inertia? It's equal to the integral of mr squared. So we have m times L squared. The second mass is m times quantity 2L squared, and the third one is m times 3L squared. So you 9 and 4 and 1, you add them all together, that's 14 ml squared. Fun fact. And a meter stick of negligible mass, no one ever cares about the mass of my meter stick, is placed at a fulcrum at the 0.4 meter mark. A lot of numbers here. Okay, 1 kilogram, 0.5 kilogram, 1 meter mark. Definitely got to draw a picture for this guy. Hey, where did those weights? Oh, yes, the weight is equal to mass times g. G is approximated as 10 meters per second squared, and now we get to use torque is equal to R cross F. Torque is equal to the perpendicular force times the radial displacement to the fulcrum, and then we multiply 10 times 0.4. And we multiply 0.6 times 5, and we notice that they're going in opposite directions, so 4 minus 3 is 1 Newton meter. And again, going a little off screen, you guys did so well on this test that it's hard for me to, I got to make it more difficult. They said that the torque about the fulcrum is 1 Newton meter. What about the torque around the center of mass of the meter stick? Well, the torque, fun fact, that's a rigid meter stick, don't you know, is the same everywhere. Here we have the fulcrum pushing up with 15 newtons, 10 plus 5. Net force has to be, we don't want this, that has to be 0. We don't want this thing accelerating up or down. Don't be crazy. That would be crazy. Anyway, calculate for yourself the torque about this point, or the center of mass of the meter stick, it's negligible mass, or this point, or that point, and you'll convince yourself that the answer is always 1. We got a double question here, 7 and 8 together. The center of mass of a cylinder of mass m, radius r, and rotational inertia I is 1/2 mr squared has a velocity of the center of mass v cm. It's rolling without slipping, that's key, without slipping along a horizontal surface, and encounters a ramp of angle theta. But we don't care because we're talking about energy here. We're talking about energy when you're talking about the maximum height the cylinder reaches. This is an energy problem. Anyway, we have kinetic energy converted into gravitational potential energy. Two types of kinetic energy, the 1/2 mv squared and the 1/2 I omega squared. And 1/2 I omega squared, of course, cleans up very nicely. We have I is 1/2 mr squared, and omega, v equals omega r, so omega is equal to v over r, and the r's cancel out, and the m's combine, and 1/2 and 1/4 is 3/4. And what were we asking for? Yeah, height. Height is equal to 3v squared over 4g, and that is, as you can see, option D. On to number 8. It's the same sort of thing, but number 8's more wordy. Now, the cylinder is replaced with a hoop. Cylinder is now a hoop. It has the same mass, same radius. The mass cancels out, but same radius. The hoop's rotational inertia is mr squared. Well, we don't really care about radius either. Anyway, the hoop's rotational inertia, mr squared. The center of mass of the hoop has the same velocity as the cylinder when rolling along the horizontal surface, and the hoop also rolls up the ramp without slipping. How would the maximum height change? Well, we have this sort of situation. The translational kinetic energy plus the rotational kinetic energy is equal to, is converted into gravitational potential. What you're telling me with this new I equation, mr squared, no more half, you're telling me that k rotational is increasing. The rotational kinetic energy is increasing, and if you do that, then you'll increase your gravitational potential energy, and the answer is A. Most people said C, which is the opposite of what's true. If the rotational kinetic energy increases, the gravitational potential, the height will increase. We kind of did this backwards in class. We did this where we let both of them go, and we said the cylinder we let them go from the same height, and the cylinder is faster and the hoop was slower. And if you sort of turn that around in your head and say, well, let's imagine they're going the same speed, which one would get up higher? Well, that would be the hoop. The figure above shows a uniform bar of mass m resting on two supports. A block of mass 1/2 m is placed on the bar twice as far, okay, I'll write that down, twice as far from support 2 as support 1. If F1 and F2, okay, I'm confused already, so let's just talk about F1 and F2. If the bar is pushing on the supports are pushing on the bar, and then we've got these two different masses, and already I can see that F1 plus F2, the upward forces equal the downward forces, so we're good. But what are we looking for? We're looking for the value of the ratio F2 to F1, and that means we're going to have to go to rotation. I'll take the left-hand side as the rotation point, and tau equals F perpendicular times R, so that means we have 1/2 mg times a distance x, and then we have the weight of the bar is 3/2 x. Notice if the total bar is 3x long, then that's halfway to the center of the mass of the bar. And then we have F2, and then we can solve for F2, and that's exciting because we have this other equation, and then we can solve for F1, and that's exciting. And then the ratio of F2 to F1 involves fractions. You like fractions, don't you? So again, here we have a two-step problem. If that bar is balancing, then the forces balance and the torques balance too. The radius of a collapsing spinning star, assumed to be a uniform sphere, decreases to 1/16 its initial value. What is the ratio of the final rotational kinetic energy to the initial rotational kinetic energy? Well, we've got three things going on here. Moment of inertia proportional to radius squared. That's the equation for a uniform sphere, but yeah, proportional to radius squared. Angular momentum, I omega. This stays the same because there's no external torque on the system. Rotational kinetic energy, I omega squared. So let's work through this. The new moment of inertia is smaller by 16 squared. That means that the omega is bigger by a factor of 16 squared, and both play a role in rotational kinetic energy. I makes you smaller, omega makes you bigger, but it's omega squared which makes you bigger more than you get smaller. See? The rod shown above can pivot about point. I didn't include the rod here. X equals 0 and rotates in a plane perpendicular to the plane. Its linear density, lambda, increases with x such that lambda of x is equal to kx, where k is a positive constant. Determine the rod's moment of inertia in terms of its length, L, and total mass, M. Totally skip this question if you get a question like this on a multiple choice. And when I say skip, just take a guess there. It's a multiple. We'll do it in a second, but I have a feeling that there'll be a question like this on the open response, the free response part of the test this year. And I have that feeling because I like these types of questions. That's why I don't bet on things, because my feelings usually aren't right. But here we have lambda that's linear density, mass per length, but it changes. So dm dx is equal to kx as given in the problem. That means dm is equal to kx dx. Let us integrate that from 0 to L. We'll get a total mass of 1/2 kl squared. An answer to the question nobody asked. We don't care about that. We want moment of inertia, but somebody might care about this later. So hold on to it and get moment of inertia. Integral of r squared dm. Bing, bang, boom. All right, I believe you because I don't really care. But wait a minute. We have mass, we have I, we're looking for which one of these I's works, which one of these moments of inertia is correct, and we solve for K. Can you do it? Can you do it? You can do it. Yeah, we can do it. I probably couldn't have done it in less than 80 seconds or less than 77 seconds, which is what you got per question on a standard multiple choice test.